This program is designed to be a visual dictionary to help with the planning of work areas in cleanrooms. It was filmed on location in one of the research and development cleanrooms of the company Meissner and Wurst, who build cleanrooms and other high-tech facilities worldwide. This particular room is equipped to be able to adjust the airflows, and with the aid of smoke generators and special lighting, the program visualizes the effects of different airflows and the relationship between air, the room, work surfaces, heat, and people. Particulate matter in high-efficiency cleanrooms is controlled by passing air through HEPA filters, usually in the ceiling, at air velocities to the order of 0.45 meters per second, so that the air travels to the floor in parallel streams. Any particles in the environment are picked up and carried away by the air through the floor, which is perforated. The air is then recirculated, conditioned, and filtered before returning to the room through the HEPA filters. A modern cleanroom is extremely efficient and will contain virtually no particles in suspension. It's when things such as work surfaces, tooling, equipment, the items being produced, and people enter the cleanroom that contamination will take place. To start with, the standard air velocity in a cleanroom is 0.45 meters per second, at which rate the air entering from the ceiling remains unidirectional, with a minimum of lateral dispersion. This continues all the way to the floor. Virtually all particles generated in the room will be removed by this air. If the airflow is reduced to, say, 0.35 meters per second through 0.25 to 0.15 meters per second, the ability of the room to purge itself becomes questionable. Efficiency obviously requires the highest flow rates. As some cleanrooms have solid, as opposed to perforated and raised floors, and recirculate their air through return ducts at the side of the room, we've demonstrated the effect of both this system and the full vertical laminar flow room. The difference between the two systems, with no other plant or equipment installed, is noticeable. The next experiment was to compare the difference between solid top work surfaces and perforated work surfaces under alternative conditions. The solid top behaves like this. The perforated top, like this. Many configurations were tried, for example, using a solid worktop standing on a solid floor as an island site. It's noticeable that a zone of slow-moving air is created in the center of the work surface, and air flows outwards horizontally over the surface until it spills over the edge, and a large longitudinal vortex is formed under the workstation before being taken away at the side of the room. When a perforated worktop is used, but still with a solid floor under the same configuration, air passes through the worktop, but this creates a vortex beneath the work surface. A solid worktop on perforated floor creates a mass of disturbed air on the working surface, but there's improved carry-away under the worktop, even though a vortex of turbulence is still created. The effect of perforated worktop on perforated floor needs no comment. The following sequence is self-explanatory, with the inescapable conclusion that very great care is needed when planning work areas. The relationship between work surfaces and walls, for example, is critical. The traditional long bench running along a wall with fixed returns and air from above appears to be of dubious benefit when the level of turbulence is taken into account. Leave a 10-centimeter space at the back and sides, and a material improvement is immediate. The factors which will determine design efficiency are the worktop area and its relationship to surrounding vertical surfaces. A problem is at low level, where turbulence is created, leading to dead areas which are probably rarely flushed by clean air. It's noticeable that considerable latitude is available when perforated work surfaces are used, in that even when the surfaces are fitted into a corner or are butted together, little turbulence is caused over the work surface, and certainly there appears to be very little disturbance at the perimeter of the surface. It's clear that where solid worktops are used, turbulent contamination can occur if there's inadequate separation of the various units. It's unlikely that items on the worktop would escape being contaminated by the vortices formed. There's also no doubt that work surfaces should not abut a wall. The airflow here quite obviously needs a gap between the wall and the horizontal surface in order to escape. Two factors occur. The first is the turbulence, which is generated when boundary conditions exist, and the second is that the vertical air velocity begins to reduce at about 5 centimeters away from the surface to virtually zero at the surface. As a matter of principle, no object sensitive to contamination should be placed closer than 10 centimeters to a vertical surface. Airflow will react differently when passing over different shapes. Air passed over a square section will create vortices and turbulence, and will risk contamination to be transported and redeposited. Better conditions are created when air passes over a cylindrical shape. Much less turbulence is caused, with little or no side disturbance. Particles in the air will undoubtedly be transported to the floor. The conclusion to be drawn is that materials designed for cleanroom use should have smoothed or rounded edges and corners to ensure that only the cleanest air passes over them. Equally, all open containers used in cleanrooms to hold products being processed should be designed to allow clean air to pass through with the minimum of resistance or blockage. The arrangement of materials and equipment is something which should be designed with care, not only in the sense of perforated or solid work surfaces, but also the interrelationship between the various items and the turbulence which they can cause will have a major bearing on the entrainment and redeposition of particulate contamination. It's of equal importance that any items or materials used in the cleanroom do not themselves generate contamination. The combination of poorly designed work surfaces, indiscriminate arrangement of equipment, and contaminating matter will undoubtedly lead to failures and low yields, and it's likely that no obvious causes will be traced. Let's look at the additional effect that heat will create. Heated components exist in many cleanrooms, and here are two examples. First, a hot plate with a 1 kilowatt capacity was heated to 160 degrees Celsius. In the first instance, it was placed on a work surface close to the wall. The turbulence is clearly demonstrated, and the potential contamination, not only from the heating unit, but also the work being undertaken on it, may contaminate items close by. Moving the plate from the wall has only a marginal effect, but given time, the room's airflow will accommodate the thermal effect. The second demonstration, using a Bunsen burner, needs no comment. The thermal effect is significant and is unlikely to reduce. Work requiring this type of flame or heat should be undertaken with great care and detailed placing of the adjacent workstations. Contamination by entrainment and redeposition will be very heavy. So far, we've illustrated only the room and wall areas. When people are introduced, it's their presence and the laminar boundary layer and turbulence caused by their movements which will transport contaminants. When people are added to the variables, not only work area planning comes into play, but the work practices of the person are equally relevant. It is necessary to stand or sit adjacent to a work area, but the speed and type of movements made are critical to the control of turbulence and thus contamination. The speed of movement is of great significance. Even slow movements are noticeable. When movement is fast, the vortices travel upwards, backwards and sideways and will carry contaminants for several feet in all directions. By the same token, carrying materials correctly is vital, and the design of a container has a bearing on how it's possible to carry it. To summarize, A cleanroom operating at airflows of 0.45 meters per second with full vertical, unidirectional or laminar airflows exiting through raised, perforated floors will be the most efficient in both removal of airborne contamination as well as reducing the risk of turbulence and particle entrainment. Work surfaces that are well perforated will reduce the risk of workplace turbulence, and all work surfaces should be separated from themselves and remote from vertical surfaces by at least 10 centimeters. The arrangement of equipment and materials on a work surface should be such that turbulence is reduced to the minimum, and that cascading of air from item to item should be eliminated wherever possible. All equipment used in cleanrooms should be designed to allow air to pass through it rather than bouncing off it and breaking up. The use and placement of heat sources in cleanrooms should be considered very carefully in the sense of random or continuous turbulence. And people should be trained to move and behave in such a way as to reduce to the absolute minimum the turbulence that they will inevitably cause.